Hello everyone, welcome to the second lecture for week 5. So our theme today is the concept of the centralizer of an element in a group. So let me give the definition and then we'll have a look at how it compares to other things that we know about. So our setup is G is a group with an operation star. We've got a particular element of G in mind. Okay, so the centralizer of that element is the set of all things in G that commute with that element under star. Okay, so here's the concise version. The centralizer of X in the group G is the set of all those elements Y in G with the property that X star Y is equal to Y star X. Okay, so just be really careful when you're reading the technical detail here. X is a fixed element. We're talking about the centralizer of X, and that's the set of all those Y's for which X star Y is the same as Y star X. That thing is called the centralizer of X in the group G, and it's a subset of the group G. Okay, and of course, the assertion that X commutes with Y for some Y is exactly the statement that X star with Y is the same as Y star with X in that order. So generally this thing is of interest when you're in a non-abelian group, so that there are pairs of elements that don't commute with each other. If X commutes with everything, then the centralizer of X is the entire group. If everything commutes with everything, then the centralizer of every element is the entire group, and the question of centralizers doesn't really have a whole lot of interest. So the centralizer of a particular element is the set of elements of the group that commute with that particular one. Okay, so a few remarks about this concept. First of all, the centralizer of X in G is a subgroup of G, not just a subset. So for every element X of G, the centralizer of X in G is a subgroup of G. So I'm not going to go through the proof of that. It'll be on the second homework assignment, but it's an exercise for you. Basically, the advice is to sort of follow the steps that we had to show that the center of the entire group G is a subgroup of G. Okay. Second remark is, it's really easy to confuse the concepts of the center of a group and the centralizer of an element in the group. So just to recap, the center of a group is the set of those elements that commute with everything in the group. Okay, so it's a subgroup of the group, and somehow the center belongs to the whole group. It's the set of those elements that commute with everything in sight. The centralizer of an element is the set of elements that commute with that particular element. Okay, it doesn't matter if they commute with anything else or not. So the centralizer of an element belongs to a particular element. The center of a group belongs to the whole group. Okay. Something that we can observe is that for any element X of G, those elements that commute with everything certainly commute with X. So the center of the group G is a subset of the centralizer of X. Okay. Why is that true? The center of the group G is the set of elements that commute with everything. The centralizer of X is the set of elements that commute with X. So if you commute with everything, you commute with X. So anything that's in the center will certainly be in the centralizer of X. However, there may be elements that commute with X, but not with everything. So potentially the centralizer of X in the group G could be a bigger subset than the center, but it'll contain the center. Okay. Another remark is that the center of G, the center of the group G, is the set of elements that commute with everything. That means it's the set of elements that are in the centralizer of everything. So it's the intersection of the centralizers of all the elements. Okay, so that's the distinction between the concept of the centralizer of an element and the concept of the center of a group. It's really important for the next stage of our work in this module that you kind of really have a clear understanding of these two definitions and the distinction between them. I guess the centralizer here is presented in quite a theoretical way, so let's have a look at an example. And our favorite example, go-to example for a non-abelian group is the group D6, the good old symmetry group of the equilateral triangle. It has 6 elements and it's not abelian, so it's kind of small enough that you can write down every detail, and still big enough to be interesting. D8, the symmetry group is a square, is another good example for the same reasons. But the remark here is, okay, we've had the definition of the centralizer of an element. So if you have a particular group in mind, we should be able to apply that definition and sort of look at it and see what the centralizer of our favorite element is. And the remark here, although I guess I should kind of be, I shouldn't oversell this, because in all honesty, it isn't for too many groups that you can actually write out the group table. But if you are in the fortunate situation where you have a small group and you can write out the whole table, then you can read all this information from the table, and life is kind of relatively good. If you're in a big infinite group, of course, you can't just sort of read off what the centralizer of some element is. But for D6, we can do it. So just to make sure that we're clear on the meaning of the concept of centralizer, let's have a look and ask ourselves, this group has 6 elements. We can look at the table and read off what the centralizer of each one is. So the identity element, first of all. Well, the centralizer of the identity element is the set of all elements in the group that commute with the identity element. So for each one, we can ask ourselves, does it commute with the identity or not? And of course, in all cases, the answer is yes. For the identity element, because it's written into the definition of a group, that must commute with everything. So the centralizer of the identity element is the entire group G. All of these elements commute with the identity. Okay, slightly more interesting to look at the centralizer of some other things. So if we take the rotation through 120 degrees, for example, and ask ourselves, well, what commutes with that? We can answer it by looking at the composition of the rotations through 120 with each of the other elements in both orders and just see which ones it commutes with. So rotation through 120, of course, commutes with the identity. And that's basically saying that the entry that appears here, rotation through 120 composed with the identity, is the same as the one that appears in the position that's marked by the same two elements, but in the opposite order. So these two elements are kind of opposite to each other under reflection in the main diagonal of the table. And if they're the same, it means that the two elements labeling the row and column commute with each other. So basically that means that if we want to read the centralizer of the element rotation through 120, we can look at the 6 elements in the order in which they appear on the row that labels the rotation through 120, because that's just the rotation through 120 composed with each one of the 6 in turn. We can look at the column labeled by the rotation through 120 and look at the order in which the 6 elements appear there. That's each of the other ones composed with rotation through 120. And basically, whatever positions have the same element appearing in the same position in the row and in the column, label those elements to commute with the rotation through 120. So if we read the row, we've got rotation through 120, rotation through 240, identity. Those 3 elements also appear in the first 3 positions of the column labeling the rotation through 120. Rotation through 120, 240, identity. So the first 3 elements here are the same as the first 3 elements here. That tells us that the 3 elements labeling the first row, first 3 columns, or the first 3 rows, all commute with the rotation through 120. And those are the identity and the 2 non-identity rotations, so the 3 rotations. If we continue and look at the order in which the reflections appear, in the row labeling rotation through 120, it's NNL. In the column, it's NLM. Not one of the 3 of them appears in the same position in the row there and in the column. And that tells us that the rotation through 120 doesn't commute with any of the 3 reflections, which I guess we already knew, but here it is written in the table. So the 3 elements that commute with the rotation through 120 are exactly the identity, the rotation through 120 itself, and the rotation through 240. And there they are. That's the subgroup consisting of the 3 rotations. Same for the rotation through 240. It has the same centralizer as the rotation through 120, and we can observe, obviously, that it is in fact a subgroup of D6. Okay, moving on to the reflections. If we look at TL, that's the reflection in this vertical axis. And again, same idea. Look at the order in which the 6 elements of the group appear in the row labeling TL, bearing in mind that that's TL after each of these guys in turn. Look at the order in which they appear in the column labeling TL, which is each of these in turn composed after TL, and just see which ones appear in the same position in the row and in the column. So in the first position of both the row and column, we have TL. That tells us that TL commutes with the identity. Okay, we already knew that, but we can confirm it. Second position, we have TN in the row, TM in the column. They're not the same. That tells us TL doesn't commute with rotation through 120. Third position, we have TM here, TN here. They're not the same. So TL doesn't commute with rotation through 240. Fourth position is common to both the row and column, so certainly the same entry is going to appear in both of those. That's TL composed with itself. It's the identity, and certainly TL commutes with itself. We already knew that too. TL does not commute with TM because the entry in this position, TL after TM, is not the same as the one in this position, which is TM after TN, TM after TL. So TL doesn't commute with TM or with TN. That would require that this entry would be the same as that one, and they're not. So the only elements that commute with TL are the identity element and TL itself, which really are kind of the only ones that, the ones that sort of least that we possibly could have. We knew in advance that TL commutes with itself and with the identity, and it turns out it doesn't commute with anything else. So the centralizer here is really as small as it could be. It's just a subgroup of order 2 consisting of the identity element and TL, and of course that's the cyclic subgroup generated by TL. Same for the other 2 reflections. The centralizer of TM only consists of the identity element and TM, and the centralizer of TN only of the identity and TN itself. So this is just really the list of centralizers of all of the 6 elements of D6. It's just included as an example to confirm our understanding of the definition, really. There'll be a few tasks on the next homework sheet to calculate the centralizers of certain elements in matrix groups, which can be quite an interesting task. as well. Okay, one more remark about centralizers and about the sort of structure of subgroups that we get arising from thinking about centralizers. So suppose that we have a non-abelian group, and of course, in order to be talking about centralizers at all, you really have to have a non-abelian group. Otherwise, there's not a whole lot to say, because the centralizer of every element in an abelian group is the same group, it's the whole group. So it's not such an interesting situation for thinking about centralizers. Okay, so if G is a non-abelian group, that means that the center of G is not the whole group, because not everything commutes with everything else. There are some pairs of elements that don't commute with each other. So we can take an element of G that doesn't commute with everything. In other words, an element of G that isn't in the center, and call it X. Then a few remarks. First comment is that the centralizer of X in G is a proper subgroup of G. It can't be all of G. And the reason for that is because X doesn't commute with everything. It's not in the center. So therefore, its centralizer is not the whole group. Okay, second remark, the center of G is a subgroup of the centralizer of X. That's just saying that those elements that commute with everything commute with X. Moreover, I claim that it's a proper subgroup of the centralizer of X, that the center of G can't be equal to the centralizer of X. And the reason for that is that we know that X belongs to its own centralizer, but X is not in the center. So there's at least one element that belongs to the centralizer of X, but doesn't belong to the center of G. So it means that we have this chain of proper inclusions. We've got the center of G. It's a proper subgroup of the centralizer of X, and that's a proper subgroup of G. So we've got in between the center of G and the whole group G, we've got this other subgroup, the centralizer of X, and this is true for all elements X that don't belong to the center. You can call them non-central elements, if you like. So the comment is just that, I suppose we're defining these different subgroups that are defined by their properties with respect to commutativity. But what we discover is that we actually have these kind of chains of subgroups building up inside the group. This isn't a terribly long chain of subgroups, but it is a chain of subgroups. And the final comment about that is that if we're in a situation where the groups in question are finite, then there's another kind of ingredient here. We can apply Lagrange's theorem. Okay, so if G is a finite group, then we're saying that the center of G is a subgroup of the centralizer of X. That means the number of elements in the center of G is a divisor of the number of elements in the centralizer of X. And the quotient is not 1, because these two numbers are not the same. It's a positive integer greater than 1. Same thing, the index of the centralizer of X in G, remember that's the fraction, number of elements in G divided by the number of elements in the centralizer of X, that again must be an integer, and it must be greater than 1. So if we take the number of elements in G divided by the number of elements in the center of G, that, according to Lagrange's theorem, is an integer. Okay, that's exactly what Lagrange's theorem says, but also it's the product of two other integers, namely the number of elements in the centralizer of X divided by the number in the center, that's another integer by Lagrange's theorem, and the number in G divided by the number in the centralizer of X. So what we're saying here is, because we've got this chain of subgroups, and this follows from Lagrange's theorem, I've kind of deliberately not written down the details to let you have a think about it. What we're saying is that the integer that you get when you divide the number of elements of G by the number in the center, it can't be prime. It has to be the product of at least two integers that are greater than 1, because it's the product of the index of the center of G in the centralizer of X and the index of the centralizer of X in G itself. So in fact, we get a kind of extra bit of information here just by virtue of this definition of centralizer. We learn that in a group that's not abelian, the index of its center in the whole group can't be a prime number, which is a sort of cute thing about finite groups. And remember what the index means. The index of the center in G is the number that you get by dividing the number of elements in G by the number in the center. That's an integer by Lagrange's theorem. Okay, it's also the number of distinct cosets of the center in the group G itself. So I suppose these concepts about commutativity and non-commutativity and objects like the centralizer and the center of a group, they're defined at a sort of instrumental level, just in terms of properties about commuting. But you get quite a lot of mileage out of them in terms of studying the structure of groups, especially finite groups, where you can also invoke the extra ingredient of Lagrange's theorem. So we'll stick to this general theme for a little while. Our topic next week will be conjugacy, which is closely related to these notions of centralizer and center. Okay, that brings us to this week's challenge. Just one challenge this week, and here it is. I think it is quite a challenging one. So we're in the abstract context where we have a group G and an element X of that group. And related to the element X, we're going to define a subset of G, called H of X, and it consists of those elements Y of G with the property that the centralizer of X is contained in the centralizer of Y. The first thing to do here is just kind of parse that for yourself. What does that mean? What's the criterion for membership of H of X? Basically, you belong to H of X if everything that commutes with X also commutes with you. Okay, and the problem is to show that H of X, defined this way, is a subgroup of G. And there's a remark there that might be of some use, or if it isn't of any use, just feel free to ignore it. Okay, thanks very much, everybody, and see you on Thursday and Friday. Thanks a lot.